So section 11.1 talks about something called goodness of fit test. And it's basically kind of a clever way to see if your observed values match your expected values. So what do I mean by that? Well, usually when I do this section, I've got a pair of dice available and, I sit there and roll them for a little bit, but I can't find them in my office right now. So we're gonna have to do the next best thing, which is a numerical simulation. So we're gonna think about a six-sided die and, just roll it a few times. So let me roll it once here. We got a 4, and then a 6, another 6. So cool, 3 6s in a row. Wow. The odds of that are 1 in 216. So pretty good for your instructor here. But I don't know. Usually I farm this out. So Philo, maybe you can roll those dice for me 600 times and get back to me with the results, okay? All right. No, I was just kidding. I appreciate your willingness. Let me clear this and we'll roll it a total of 600 times. Now, this is a regular six-sided die. And I want us to think about what would you expect? How many times do you think I should come up with a 1? How many times should I come up with a 2, 3, 4, 5, 6? If I'm rolling a fair die, six-sided die, 600 times, how many of them should come up with a 1?
100.
About 100, right? 1 out of 6 of those. So 1 6 times 600 should be, about 100. So let's do that. And I'm going to do it in chunks of 50 here. So I'm going to be 12 of them. Bang, bang, bang. 150, 200, 250, 300. Let's get all the way up to 600 and see how we do. So there we go. There's 600. And let's compare our results to what we expected. So we expected 100 in each of these things. And for the first one, I got 103. And then for the second one, 107, and then 102. So not bad. I mean, pretty close to what we expected. 96, 107. Let's see, 96, 107. And what's the last one? How many 6s? It doesn't look like we did too good. 85 on the 6s. So not too good there. But are these results far enough away from what we expected that you would say, no, I don't trust that die? Doesn't look fair? Or are these kind of reasonable? What do you think?
Reasonable.
They seem reasonable. All right. I mean, a little bit low on the 6s, but not bad. So at some point, though, if I had maybe only 76s or 50 of them, you're going to start to say, well, wait a minute, it doesn't look right. It doesn't feel right. My observed values are too far away from my expected values. So I'm starting to think this isn't really a fair die anymore. And I wouldn't blame you. But we need something a little bit more objective than that in order to try and decide if we think that our data matched or didn't match our expectations. So that's where we're going to form the following test statistic. It's a chi-square distribution, and that chi-square test statistic is going to be the sum over all your different categories of the observed minus the expected squared divided by the expected. This chi-squared is going to have certain degrees of freedom associated with it. So degrees of freedom is going to equal n minus 1. Now, n is not the number of die rolls that I had here. N is not 600. What do you think n is going to be referring to in this case? It's going to be the number of categories So in this case, how many categories do I have? Well, 6, right? So if we form this test statistic, it would be for a chi-square with n minus 1 degrees of freedom or 5 degrees of freedom in this particular case. our hypothesis that we're gonna be testing is gonna be much different than the hypothesis test that you're used to. So I'll give you a couple different versions of that hypothesis test. You could have H naught, could be that the observed frequencies match the expected frequencies. So that's one possibility. Or another possibility would be this. Again, HO. You could list the probabilities themselves. So you could, in this case, write probability of a 1 is 1/6. Probability of a 2 is also 1/6. Probability of a 3 is 1/6, and so on, all the way down to the last one. Probability of a 6 is 1/6. So you can do it either way. Doesn't matter to me. Now, once you have your hypothesis stated, your null hypothesis, what goes along with an HO? HA. So here's a couple different versions of the alternative hypothesis. The observed frequencies do not match the expected frequencies. And the alternative version for this H naught is going to be kind of different. It's what's kind of referred to as an omnibus alternative, kind of like a catch-all alternative. And that alternative would be at least one of the above probabilities is different. One of the above probabilities is different. So, hey, nice. Those are our couple different possible alternative hypotheses. So, all right. Let's actually practice with this one. We're not going to do it out formally here, but let's just practice with the data that we collected for our experiment. So I want to go to StatDisk and check that out. Let's see here. So for the analysis, I need to put in the data. Let me remind you of our data. So we had 103, and then 107, followed by 102, 96, 107, and then a big jump all the way down to 85. So the question is, are these far enough away from what we expected to actually cause us to reject this idea that, yeah, it was a fair die, it was being rolled all along? Now, our expected values, in this case, we don't need to list them, but I want to list them just so we can kind of look at them and help set the tone for the choice of analysis that we're going to use here. These expected values are all 100. They're all equal. And when you go up here for your analysis, you're going to drop down to something called the goodness of fit test. And then you'll have two choices: equal expected frequencies or unequal expected frequencies. Which one do you think I'm going to choose for this particular one? Equal. Yeah, we expected all these to be equal. Now you can characterize that in a couple different ways, but if they're all equal, then it makes your life of inputting things a little bit easier. We won't need that second column at all. So we'll do equal expected frequencies. And this says, okay, great. What column? We've got a significance level of 0.05, looking good there. And let's hit the evaluate. By the way, how many degrees of freedom am I going to have for this test? 5. n minus 1, 6 minus 1 is going to be 5. So beautiful. There's your critical value. So if you're doing this in the classical approach, you would actually look at the chi-square distribution with 5 degrees of freedom. This point puts 5% of the area in the tail. That's the 5% from your significance level. If your test statistic is beyond that, then you reject it, because it's very unlikely that H naught could be true and you get a test statistic out here. But that's not the way we do things. How do we do things? How do we decide if we're going to accept or reject H naught? The p-value. Is our p-value close to rejecting? Not so close. I mean, kind of see it here. Our test statistic is pretty far away from this red line. And it's also reflected here. Our p-value is very far away from the 0.05 level. We're not anywhere close to rejecting. So basically what it's saying is that, yeah, our data seem like they fit the idea that we've got a fair die. Probability of rolling a 6 or a 5 or a 4, whatever, is 1/6. So yeah, it seems like this is going to hold true. All right. But that's our null hypothesis. We don't like to really say that we're affirming this. We just say we can't disprove it. But our data is certainly consistent with that idea. So that's kind of like a little bit of a warm-up example. Let's do another one. Now there's a handout there, and I'm actually going to borrow something from a YouTube website that I saw called Mine the Data. And it's going to talk about the number of likes you get on something that's kind of new out there on the internet. Has anyone heard of this new thing called TikTok? Yeah, you're familiar with that? A couple of you? All right, it's a couple of you are pretty trendy. That's cool. All right, so how about if we would have had a data set for the number of likes on TikTok, would there be any pattern to that? Do you think that it would have any predictable pattern? So the person behind Mine the Data was kind enough to actually share the data with me. And here it is. We got over 5,000 different YouTube videos, and they downloaded the number of likes for each of these videos. Do you think there'd be a pattern here someplace? Something that you could predict without really knowing anything about this data set? Is there something I can predict? Turns out there is. There was a researcher by the name of Frank Bedford who worked for the IBM Research Center back in like the 30s. And back then, they didn't have nice computers and calculators like we do now. You had to look things up on a table. And what he noticed is that a lot of the early tables, the early pages, were a lot dirtier, meaning people were referring to those more often than they were to the later ones. And he finally figured out that there's a little bit of predictability about the leading digit. So what page you're going to turn to. Do you want to see a leading digit of 1, a 2, all the way up to 9? Those probabilities aren't the same. And those probabilities are given by something called Benford's law. Now, if you want to know how these actual probabilities are calculated, let me tell you, it's pretty easy. So we'll call this Benford's law. Probability that X is your leading digit is the log of 1 plus 1 over X. That's it. But it turns out that it means that all leading digits are not created equal. There's about a 30% chance that in your data that your leading digit is going to be a 1. And then maybe a 17% chance that it's going to be a 2. And all the way down to a 9, which has less than a 5% chance of being a leading digit. Do you think TikTok data is going to satisfy Benford's law? Anthony's a little skeptical. Say, nah, it just feels too weird, which I don't blame you. Benford's law is not something I heard of until I got to graduate school. So let's see how it does. And you've got a handout with some output on that. Let me see if I can pull up the right thing here for us. So here's Benford's law and those probabilities. So 30%, 17.6, 12.5. And then here's a plot of the actual data that we picked up from this website, Mind the Data. And that's looking pretty close there. Those values look pretty close. So to help us out here, let's do the analysis. I think I gave you a link to some data sets. And that data link is on our website. So when you click that, it should open up this one. And these are the two columns that we want to choose. I want to choose the P of X, the probability that comes from Benford's law, and then the observed, I guess I'll need to do this one at a time. I'll choose the P of X, this column first. Can anyone tell me what the 1 is down at the bottom? Yeah, probability of everything is 1. Your probability distribution should always add up to 1. Let's paste that one in there first. So let me clear out this data here. Paste that one in here. And then go back and catch the other one. I want the observed frequencies. Now take a look at these probabilities. Are they all the same? Are all these probabilities like 1 out of 6? No, they change. There's a lot of variation in those probabilities. That's going to become important as we input our data. Let's input those counts there. As far as the rest of this is concerned, let's actually run through the steps of a hypothesis test. So for Benford's law, I'd probably do something like this. So step 1, the null hypothesis is that this probability of a leading digit of 1 is 30.301 or 30.1%. Probability of a 2 is a leading digit is 17.6%. And I'm going to get pretty bored with this real quick. So we'll just do ... all the way down to P sub 9 is 0.046%. Now with this form of the null hypothesis, then the alternative hypothesis that we're going to use is at least one of the above probabilities is different. At least one of the above probabilities is different. I put than claimed. And the only reason I'm putting this here is because I want to be specific that if we're going to conclude HA, I'm sorry, I should have an HA there. If we're going to conclude HA, then we're really saying one of these is wrong. We're not sure which one, but at least one of those is wrong. What's our typical second step when we're doing a hypothesis test? Setting, say again? Significance level. Thank you, Skylar. So what do you want to choose for alpha here?
0.01.
0.01? Okay. Setting the bar pretty high. Want this to be very accurate. Good. The third step for us is inputting the data. We got that done. What's the fourth step? What do we want to do here? Yeah, we want to find the p-value. So for that, we're going to go to StatDisk. You're going to click Analysis, and then go down to Goodness of Fit. You've got two choices here. Do I want equal expected frequencies or unequal expected frequencies? Unequal. The probabilities are different, so the expected frequencies are going to be different. We got to change our significance level to 1%. The expected values are listed as proportions. Now, synonyms for this would be fractions or ratios or percentages, probabilities. So there's a lot of different ways you could say this. One thing I will say about StatDisk is that it doesn't like it if you type in a fraction. One of our problems later on, one of the probabilities is 2/16, but it's not going to like that. Might look at that as maybe a date or something like that. You have to type it in as 1/8, which is 0.125. That's what it'll be looking for. All right. Where's our observed column? What's that one? 2. Those are our observations. And then column 1 has our expected proportions. So looking good there. And I think we're good. Yeah, question?
Could you go back to Google Sheets? So
This is the total. That just says
what about C, or what about
column C. Oh, this is just something I did to calculate the actual observed proportions. We're not going to use that in our analysis, but you can see that our observed values, our observed proportions are pretty close to the predicted ones, right? So I did that just to look at things. I mean, these are really close for some, I mean, this is TikTok data, so it's pretty random. Yes.
Just for clarification on this upcoming exam for this portion, 11.1, for the H null and alternative, are you gonna want us to write out like all of the expected, or can we like?
You can do the little ... like I did. That's fine. Yeah, I don't need you to write all that out. I don't really want to make you write all that out. Adel?
you're putting expected frequency as proportion of C.
C is the observed proportions. It's not the observed frequencies. So we need to put in the observed frequency here. So that's what we're gonna concentrate on. I just, like I said, I did this just for giggles to see how this compared to what we expected. And it's amazingly close. And I was pretty impressed. So let's actually finish up the hypothesis test then. Let's see, just basically click evaluate. Bam. So step 4 is to find the p-value. Chloe?
It's not letting me click the data in StatDisk. Like I have it, but it just keeps saying.
Sometimes what happens when you copy the data from, say, Google Sheets over to StatDisk is you accidentally copy a blank character somehow. So maybe if you copied this and then you deleted that, there would still be a blank character here. So if you're getting something that says, oh, your columns are of a wrong length or something like that, one thing you can try is to clear all your data and then paste it in again, and be really careful just to paste the exact values that you need. So that might do it sometimes, but if that doesn't work, let me know and I'll try and swing by at some point and see what's going on.
Okay, thank you.
All right. Let's go back to the analysis here. Let me redo it real quick. Goodness of fits, unequal, 1, 2. Does it really matter if I put this as 0.05 or 0.01? Let's see, do I have this right? No, I don't. That's backwards. So my p-value is 0.7146. What's that going to say in terms of step 5? Are you going to accept H naught or fail to reject H naught or reject H naught? Fail to reject. Good. Fail to reject H naught. Would it have mattered if I had a p-value or alpha of 0.05? No. Am I anywhere close to rejecting? Now, so it's kind of implying that Bedford's Law is actually a really good fit for this because this is so big. It's very consistent with the null hypothesis. Finally, state the conclusion in words. There is not sufficient evidence to reject the claim that the number of TikTok lights the number of TikTok lights follows Bedford's Law. All right. Nice. Nice. Okay. Feeling comfortable with that first one? All right. Let's try some more here. So the next one is not going to require us to input any data at all, but there is something in particular that I wanted to highlight about that. So let's see if I can't get this to roll up a little bit. There we go. A random sample of 780 subjects was asked to identify the day of the week that is best for quality family time. Consider that the claim that the day of the week are selected with a uniform distribution. Well, we're going to talk about what that means. And basically that means, like they say over here, so that all the days of the week have the same chance of being selected. So to say it pretty clearly there, the table below shows the goodness of fit test results from the claim and data from the study. Test the claim using either the critical value method or the p-value method. Assume a significance level of 0.05. All right, so let's see if we can't put the claim into words. Now, the important thing to notice here is that the original claim is talking about the same chance that people would pick Monday as the best day for quality family time as it is Friday or Saturday or Sunday or any other day of the week. So let's see if we can't put that into a probability. So H naught. If the chance of you picking any day of the week is the same as all the other ones, what's the probability that you'll pick a Monday? 1 in 7, which is the same as you pick a Tuesday or Wednesday or Victoria. There you go. ... All the way down to probability of a Sunday, and that's 1/7. Great. So here's our first step. The alternative hypothesis. Has anyone got this down yet? What am I going to write for HA? At least one of the above probabilities is different.
Is that our H alternative for all of these?
Yeah, I mean, I gave you a couple different H alternatives. It kind of depends on what you use in HO, but yeah, I mean, this is fine. At least one of the above probabilities is different. We will see an example D, a different example of something like this. One of the probabilities is different. And something is compelling me to say than above or than claimed above. And the only reason I'm adding this is because somebody in my morning class was a little bit unclear about what was different, and it's one of these probabilities is different. what bothered me when I was in graduate school, when I was looking at these kinds of things, is that it really can't just be one of them different. It would have to be two of them different, but this is the way we state things, so I've stopped fighting it years ago. What's our significance level for this test? 5%. Good deal. And they've already entered the data for us. So that brings us down to this step, step 4. The p-value. Cody, what's the p-value for this one? Yeah, basically 0. So 0, good deal. P-value 0. So Jacqueline, what's that going to mean for our hypothesis test?
You would reject H0.
Reject H0. Excellent. Keisha, why am I rejecting H0?
Because the p-value is less than this.
Beautiful. The p-value is less than the significance level. Excellent, excellent. Now, is it a surprise? I mean, is anyone surprised that not everyone's picking the same day of the week with equal frequencies, or different days of the week with equal frequencies? And what's your inclination? Where do you think most of the people are going to be picking? Yeah, the weekends. So it's not a big shock that weekends are going to be more frequent. Let's see. So there's sufficient evidence to reject a claim. Is sufficient evidence to reject the claim at the day of the week chosen for quality family time should put days of the week. Yeah, I missed out a word here. Days of the week chosen for quality family time are equally likely. So we got rid of that. It's not true that they're equally likely.
Sheet that you said you were giving us.
I
Kind of like.
I am framing it like the sheet that we had for wording the hypothesis conclusion.
Okay.
And it's just to kind of keep things familiar with you. So a lot of times what you see me to do today is treat this as if it's always the original claim, and then either say the data fail to reject it or reject it. So, and for that, you can always go back and look at the wording in the problem itself and try and get some hints as to exactly what you want to say. That the days of the week are selected with a uniform distribution. That would have been fine. Maybe even a little bit better. Jacqueline, did you have a? No, okay. Yes.
Lost my sheet, where is it on each logo?
If you do a search in the content area, just search for wording, type in wording, might be able to find it there. Sure. All right, let's keep going. Any more questions on example B before we get to example C? So I don't know why I didn't do this earlier. But I think it's working out pretty good. And that is, if you follow that link for Google Sheets, after you go to the Benford's Law example, we can do the data for example C, which is this one. talks about the winning position of the horses in the Kentucky Derby. So here's the statement of the problem. Table below lists the frequency of wins for different positions in the Kentucky Derby race. Position 1 is closest position to the post or the inside rail, so that the horse has the shortest distance to run. Because the number of horses varies from year to year, only the first 10 positions are considered in this data set. Use a 5% significance level to test the claim that the likelihood of winning is the same for the different post positions. So let me highlight that a little bit. Likelihood of winning is the same for the different post positions. All right. So let's see if we can't turn that into an alternative hypothesis. So let's see. Example C. Now remember, there's 10 riders and 10 horses in this race. If they each have an equally likely chance of winning, what's that chance? 1 out of 10. So that means probably the first one wins. Same thing as probably the second one wins. Third one. And then the ... We'll shoot that out to Victoria again. All these probabilities are equal to 1/10. The alternative hypothesis is at least one of these is different. At least one of the above probabilities is different than claimed. Okay. That's good. Step 2, and I hope, like I said, you're kind of catching a rhythm here. Step 2, what are we at step 2? Alpha is 0.05. Step 3, we got to input some data. Now you can copy both columns here if you want. We're not really going to need both columns though. You can copy them both if you want. Copy them from Google Drive or Google Sheets over to your stat disk. Let's clear out the old data there. Paste in the new data. And then go over to the analysis. Analysis, goodness of fit. I've got 2 choices here. Which one do I want? Equal. Now, if it's equal expected frequencies, Statist is just going to divide everything up and say, oh, I've got 10 categories. That means each one has a 1 in 10 chance of winning, and it's going to do the analysis based on that assumption. So all I need to do then is put in the observed column, and that's in column 2 for me. I'm not sure where it is on yours, but it's in column 2. 5%, bang. There's your results. Anything, Esther, are we going to reject H0 or fail to reject H0?
Fail to reject because it's not.
All right. Fail to reject because it's not less than the p-value. Ben, do you agree or disagree? What do you think? Looking good there, Chloe? Fail to reject or reject? Yeah, let me go back over. Yeah, sorry. Here, there you go.
Oh, yeah. Fail to reject.
Yeah, fail to reject. If your p-value is greater than alpha, you're going to fail to reject. Perfect. So p is greater than alpha, fail to reject. H naught. Now, am I a little closer to the rejection region in this one than the last one? I mean, excuse me, this one than maybe I was in Benford's law? Yeah, I'm closer, but I'm not close enough that I'll actually start considering anything. But yeah, we're gonna fail to reject. Finally, it's state your conclusion in words. Let's see. There's not sufficient evidence to reject the claim that the likelihood of winning is the same for different post positions. There is not sufficient evidence to reject the claim that the likelihood of winning is the same for different post positions. Nice. Nice. All right. Hopefully we're doing okay there.
Question.
Please do.
So how do, I guess I'm confused on when she used the different, tests. Like, why did we use equal expected frequencies instead of,
So when you get down to here, which one do I choose?
yeah,
All right, good question. So equal expected frequencies is going to happen when all your probabilities are the same. So days of the week, all 1/7, finishing position, all 1/10. All of those probabilities were the same. So that means your expected values are also going to all be the same. So if you have equal expected frequencies, that's the same as equal expected values or probabilities. Now, if we look back at our Benford's law example, those probabilities were all different. You see those probabilities here and on your sheet, but those probabilities were anything but equal. So that's why we had to enter 2 columns of data. We entered those probabilities, and we also entered in the observed values. You're going to need to enter in those 2 things. If, as in the case of some of our data that all the expected values were equal, then you just need to enter in 1 column and statistics will figure out everything else for you. So you're welcome. In fact, in regard to that, let's kind of veer off script a little bit here. And I've got some data here for M&Ms. And I want to show you a little bit of something on Google Sheets, etc. Don't worry about it. If you want to learn a little finesse trick about Google Sheets, then pay attention to it. Otherwise, don't worry about it. But this is our M&Ms values from earlier in the semester, where we had different colors of M&Ms. We open up a bag. Actually, I did that for both my morning class and for my afternoon class, and got these totals, etc. The true probabilities were given to us by M&Ms. Are these probabilities all equal? No, they're not. So we're gonna have to enter in some different columns of data. So here's our true probability again. If I wanted to figure out the expected values, then what I could do is take the total number of M&Ms from my 2 trials and multiply that total by this probability. So, okay, not a bad thing there. And I'll do the first one like this. I'll do equals, and then I want this probability times this number here. Okay, that's my 132. So if I had 132 M&Ms, I'd expect roughly 17 of them to be whatever color this was first here. 17 would be red. Now, what we've always done is we've dragged this down and let it fill everything out. But wait a minute, it's not working. The reason it's not working is because when you drag it down, then this cell also gets dragged down. So the next cell it's looking for when it does this calculation is blank, it's a 0. But they have a little fix here. So let's go with the fix. Let's see, yeah. And what that fix is going to do is it's going to lock this one. It says, all right, if you want to lock this one so that it doesn't change, then take a look at the formula. It puts a $sign in front of the E, so it locks the column, and then it puts a $sign in front of the 11, so it locks the row. And now you can copy and cut all the way down. So here's our expected values. So we can see how those compare to the actual observed values here. And I'll put them adjacent columns. That's not right. Copy, paste. Why is it doing that? Copy. I'm not sure why it's not just copying those. That's what I wanted. Let's do paste special. Values only. There you go. So our observed values aren't really far away from our expected values. Well, this one's not too good. This one's not so good. So let's see if we got an unusual batch of M&Ms. Are our observed values far away from our expected values? So let's write down some probabilities and do a hypothesis test. So kind of veering off script a little bit. This is example D, or what's going to pass for example D. Maybe I'll call it example M&M. Our null hypothesis is going to be that these probabilities are all in place. So the probability of a red is 0.131. Probability of an orange is 0.205. And we'll just do what we've been doing all along. Skip down to the happy ending. Probability of a brown is going to be 0.124. Our alternative hypothesis is that at least one of the above probabilities is different than claimed. And if you want to take a gander at what I'm writing, it's nothing different or unusual. At least one of the above probabilities is different than claimed. So that's step one. Step two. What should be our step two? Significance level. Anthony, what significance level should we choose? One more time. 0.01. All right. 0.2 on my black pens here. And let's input the data. Now, even if you didn't play around with the data like I did here, you still should have the M&M's example. So you can copy down two things. You want to copy down the totals here, your observed totals, and the true probability. You can get those both at once. Let's paste them into StatDisk. Clear out your old data set. Put in the new data set. And let's run an analysis. Goodness of fit. Which one of these should I choose? Unequal. Our probabilities are clearly unequal. The observed column is the first column, expected column is here. And I think that Anthony said we want to do 1%, so let's do that. Ooh, wow. This like hardly ever happens. What are we seeing happening? All right, well, we'll get there in little bitty steps then. What's step 4? Felonious? What's step 4 for us when we do these kinds of things? Will help? Yeah. So the p-value is 0.00538. 0.00538. Let's bring up to step 5. Demetrius. What's that suggesting? What do you think surprised me about our p-value? Yeah, you reject H0. Wow. Yeah, that like hardly ever happens. I've been doing these M&M experiments since 19 mumble, and it's rare that you see that your data doesn't fit their distribution, at least not close enough. So pardon me if I'm a little giddy at the moment. It's kind of cool. All right. In any case, so there's sufficient evidence to reject the claim that M&Ms gave me a really well-mixed bag of M&Ms. They didn't. Somehow or another, it wasn't up to par. All right, but let's think about how I really want to say this. There's sufficient evidence to reject the claim that the probabilities from M&Ms are correct, or let's see, let me think one more time. There is sufficient evidence, bless you, to reject the claim that the distribution of M&Ms is I don't want to write this. Is I don't want to be too long is what I'm debating here. So I just kind of want to briefly refer to these probabilities up here is what I'm going to write. Any suggestions? Is the same as the above probabilities. Yeah. As the above probabilities. I mean, I do want a nice accurate statement down here from you, but I don't want to make it unduly long. So that's why I was struggling a little bit there, trying to come up with something of a reasonable length, but it also refers back to the original problem. Okay. All right. Let's do one last one. Unless you guys are feeling pretty good about this.
One more.
One more? All right. So let's move on to example D. So this is actually a good one to do because it'll give me a chance to show you something about these proportions here, these expected proportions. The table below lists the number of games played in the best of 7 baseball World Series, along with the expected proportions for the number of games playing with teams of equal abilities. So basically, that teams of equal abilities stuff really has nothing to do with your null hypothesis. It seems like it does, but it's the way they came up with these probabilities. So if the teams were evenly matched, you know, if it was just a coin flip as to who's going to win, then this is the proportion of times that you would expect the series to be over in 4 games, in 5 games, in 6 games, and in 7 games. So that's what they're using this little bit about evenly matched to come up with, is these probabilities. Use a 5% significance level to test the claim that the actual number of games fit the distribution indicated by the expected proportions. So, okay, that's fine. Let's do that. Now, instead of stating something in their null hypothesis about probabilities, we're actually going to do something a little bit different here. Our null hypothesis is going to be that the observed frequencies agree with the expected proportions, or at least one of the observed frequencies do not agree with the expected proportions for your alternative. So you can do, you know, whatever strikes your fancy when these things. We're just changing things up just to show you a little bit of variety. Example D. And I'm just going to copy down these things right here, our HO and HA. The observed frequencies agree with the expected proportions. And finally, the alternative hypothesis is that at least one of the observed frequencies does not agree with the expected proportions. Okay, so let's go back to here. We're going to test this at the 5% significance level. Sounds good. Alpha is 5%. So that's our second step. Here's our first step. As far as inputting the data is concerned, again, this is something I have already put in for you at Google Sheets. So if you just click this little fold here, you should be able to jump down to example D, and you want to copy the observed and the expected. Now, the reason I put this stuff in over here is just to remind you that you want to use decimals, not the fractions. If you try and put stuff in like this into StatDisk, it's going to give you an error. It's just not going to like it, which I don't completely understand. I mean, it feels like it's simple to accept fractions, but I don't know. I'm not doing all the programming behind the scenes, so what do I know? In any case, copy down the expected proportions in terms of decimals. Let's go back and enter our data, clear out this other stuff. There's your data. Johnny, which one of these do I want to choose?
Unequal.
Unequal. Nice. The probabilities here are different. So unless the probabilities were all going to be the same, then you're going to choose unequal. Thank you, sir. Observed columns in 1, expected columns in 2. 5%. So let's hit evaluate. Nice. So our third step was to put in the data. Fourth step. What do I need from the fourth step, Justin? P-value. All right, so the p-value 0.1222. Good enough. Clara, what am I going to do with my null hypothesis?
Fail to reject.
Excellent. Fail, reject. Mikhail, why are we failing to reject? P is greater than alpha. P is greater than alpha. Beautiful. And finally, you want to state your conclusion in words. There is insufficient evidence to reject the claim and here's not a bad idea to go back and take a look at the original problem. For two reasons. One, if you go back and look at the original problem, what you're right will be relevant. And two, it's just less thinking. We can just state what the original claim was directly from the problem. You'll keep me happy. You'll keep you happy. So let's take a look at what that was. The actual number of games fit the distribution indicated by the expected proportions. Beautiful. So let's go with that. The actual number of games fit the distribution indicated by the expected proportions. Perfect. All right. Looking good on that one. Beautiful. Anything else here on section 11.1? All right, let's call it a wrap. Put this one in the books.